I'm going to define a simple function given by the length of a particular sequence. It's called n of k, and as it happens, n of 1 is 3, n of 2 is 11, and n of 3 is, well, as the inventor of this function said, n of 3 is incomprehensibly large. Mathematician Harvey Friedman invented this very simple function in his innocently named paper, Long Finite Sequences. We'll leave a link in the description. And if you're thinking that a Google to the Google factorial power all times a Googleplex squared is incomprehensibly large, then you have no idea just how big these numbers can get. Now, this paper has everything. It has big numbers, really big numbers, super cool, short, elegant arguments, but the one thing that's missing is calculus of any kind. Now, I love calculus. It's not like I wear it on my sleeve, but you don't need to know one iota about epsilon or delta or limits or analysis. So first, we'll introduce a special type of sequence of integers that is the basis for this n function. We'll show these sequences are always finite in length using a super clever discrete argument. Again, no calculus here. We'll introduce a result about graph theory called Konig's lemma, which you might think is completely obvious, or if you're like me, you might suspect it's obviously maybe wrong. And I'll show you a quick, elegant proof of it. Then we'll show how this relates to Friedman's special sequences and why this proves that his n function is actually well defined. In the next video, we will give you the most enormous lower bound for n of 3 you can imagine. Except you won't be able to imagine it, since, as you'll recall, n of 3 is incomprehensibly large. And if there's demand for it in the comments, we will make a third video proving that n of 3 really is that big. That proof is a clever argument on steroids, and it deserves a video of its own. So here goes. Start with a set of integers from 1 to k. We want to form a sequence of these elements, repeats are definitely allowed, and let's say the terms are a sub 1, a sub 2, a sub 3, and so on. Now let's pick I and j to be integers where I is less than j, and there are at least 2 times j elements in our sequence. Look at the string of elements from a sub I to a sub 2i, and the string of elements from a sub j to a sub 2j. If we can find such an I and j where the first string is a subsequence of the second string, then we say that this is a bad sequence. An example or two should help clarify this. This sequence has 9 elements, and if we take a sub 2 through a sub 4, and a sub 3 through a sub 6, we get 3, 3, 2, and 3, 2, 3, 2, and that first string is a subsequence of the second one. It's not a consecutive sequence, but we do preserve the order of the terms in the first string, and that's what matters. So this is a bad sequence. To take another example, we can take a sub 3 through a sub 6, and a sub 5 through a sub 10. The first string is a subsequence of the second string, so we have another bad sequence. In this sequence, we can look at all the strings of the form a sub I through a sub 2i and list them out. And you can check that none of these strings is a subsequence of a later one. For instance, none of the entries below 1, 3 have a 1 followed later on by a 3, and none of the entries below 3, 2, 3 have a 3 followed later by a 2 followed later by a 3. Any sequence that isn't bad, we'll say, is a good sequence, so this last example is a good sequence. The n of k function is defined as follows. Take the set of integers from 1 to k, this is called our alphabet, and find the longest good sequence using just those numbers. N of k is the length of that sequence. It's not clear that this is well defined. The longest good sequence, for all we know, could be infinitely long. And even if there are no infinitely long good sequences, there could be arbitrarily long ones. So maybe there's a good sequence of length 100, another of length 1000, and another of length 10,000, and so on. Our first big result is that there are no infinitely long good sequences. It will actually be easier to tackle a more general problem. This happens every so often in mathematics where it's easier to prove a stronger result than the one you're targeting. For instance, if you had to prove that 2x cubed minus 16 all divided by 4x squared was continuous, it would be a royal pain to do a traditional epsilon delta proof. Instead, you could save yourself some aggravation by showing that y equals x is continuous and that multiplying and dividing continuous functions yields new continuous functions, at least when the denominator is non-zero. Oh wait, I said no calculus. Okay, how about this? If someone asks you to prove that this weird-looking identity that the square of the sum of the first n positive integers equals the sum of the cubes of those same integers, you could tie yourself in knots trying to come up with a direct argument. Or you could just prove the two well-known facts that this sum is n times n plus 1 over 2, and this sum is n times n plus 1 over 2 all squared, and you're done. So in the case of good sequences, we want to eventually show that none of them have infinite length. Well, if we're given a good sequence, then we can make a table of all the strings that we have to check. So first write down the string a sub 1, a sub 2, then the string a sub 2 through a sub 4, and in general a sub j through a sub 2j. Now we just have to make sure that none of these strings is a subsequence of a later string. We're actually going to prove the much more general result that if we're given any sequence of strings where no entry is a subsequence of a later entry, then that sequence cannot have infinite length. In other words, take any sequence of strings, not just one that's generated by extracting elements from a sequence of single characters. If this general sequence has the property that no element is a subsequence of a later element, then the sequence can't be infinite in length. For some terminology, we'll say that a sequence of non-empty strings is compliant if no string is a subsequence of a later string. I'm saying compliant just to differentiate it from the way I was referring to sequences of characters as good earlier. We are going to prove that there are no infinite compliant sequences of strings, regardless of whether or not it was generated by looking at a sequence of single characters. Here it goes. Let's assume there are infinite compliant sequences. We're going to find a minimal sequence in a certain sense. Of all those infinite compliant sequences, some of them have a first element of minimum length. Maybe there is an infinite compliant sequence where the first element is a string of length 1. If so, grab that first element. If not, there might be a sequence where the first element has length 2, and we could use that one. In this hypothetical example, there are sequences where the first element has length 3, so let's pick the first term from one of them. Now, there may be different infinite compliant sequences with that string as the first term. Of all those sequences sharing that first term, in this case 3, 1, 2, pick the one with the shortest second term. Here we can go with either the string 1 or the string 2. Well, let's grab 1. And then of all the infinite compliant sequences having those strings as their first two terms, pick the one with the shortest third term, and so on. That's our, quote, minimal sequence. Now, it probably won't surprise you to learn that we're going to reach a contradiction by constructing another infinite compliant sequence that's, quote, smaller. Here's how we do it. Our minimal compliant sequence has infinitely many terms, but there are only k elements in our alphabet, so some symbol must occur as the initial character in infinitely many terms. Just to make things specific, let's suppose that infinitely many terms start with a 5. Let's say the first n terms don't start with a 5, and then the n plus first term does. We're going to construct a new compliant sequence as follows. Keep the first n terms intact. Next, starting with the n plus first term, only take those terms that start with a 5, but strip off the initial 5. Now, I'll quickly point out that none of these elements is just the single character string 5. If that were the case, then 5 could never occur again in a later string. After all, the single character 5 would be a subsequence of it. So when we remove the 5 at the beginning of these entries, we don't end up with an empty string. Anyway, this new sequence is still infinite in length, since we assume there were infinitely many terms starting with a 5. But we also claim that this new sequence is still compliant. To see why, just grab two terms and see if the earlier one is a subsequence of the later one. If the two entries are both within the first n, then these were just copied down from the original sequence. If the earlier one wasn't a subsequence of the later one before, it certainly isn't one now. If you compare two terms from after the first n elements, then you're just looking at two strings that used to have an extra 5 in the first position. If the first entry is a subsequence of the second one, then it was also a subsequence earlier when the 5s were in front. Okay, what if you grab one entry from within the first n, and another entry from past that point? Keep in mind the first entry is unchanged from earlier, and the later entry just had its initial 5 removed. Since the first entry did not have a 5 as its first character, then it makes no difference that the initial 5 was removed from the second entry. If the first string is a subsequence of the second, then it was earlier too when there was a 5 in front. So this new sequence is still compliant, still infinite, and since the first n terms match our original sequence, but the n plus first term is shorter, we have a contradiction. The conclusion is that there are no infinitely long compliant sequences of strings from a finite alphabet. This also tells us there are no infinitely long good sequences of single characters. So just to recap the argument, we start by assuming there is an infinite good sequence of single characters. So the string from a sub I to a sub 2i is never a subsequence of a sub j to a sub 2j. This means we can turn this into a sequence of strings where the ith entry is the a sub I to a sub 2i string from the sequence of characters, And this new sequence of strings is an infinite compliant sequence. So then we just needed to prove there are no infinite compliant sequences. If there were one, we could pick the minimal one in the sense that given the first n strings in the sequence, the n plus first string is as short as possible. Then we said there must be some character that's used infinitely many times as the first character in these strings. Then we used this to construct a new compliant sequence that was smaller than the minimal one, which is a contradiction. We're about halfway through, so this would be a good time to mention that it is a lot of fun for Nick and I to make these videos, and it is also a ton of work. This is a fledgling math channel, so it would really help us out if you support us by subscribing, clicking on the thumbs up, and sharing this with your math friends. And if you don't have any math friends, then share it with your physics friends. And if you have neither, then you have my condolences. Okay, back to the math. Let's talk some more about sequences of strings. We now know there are no infinitely long compliant sequences of strings. But is there a longest compliant sequence? Well, no. You can make these as long as you want. Even with just a single character in your alphabet, if you wanted a compliant sequence of length 3, then start with 1, 1, 1, then 1, 1, then 1. If you want a compliant sequence of length 5, just start with 5 ones in a row, and so on. 4 ones in a row is certainly not a subsequence of 2 ones in a row, for instance. If you have 2 characters in your alphabet, let's say 0 and 1, and you wanted to make a compliant sequence of length, say 2 to the 5th power, you could just count from 0 to 31 in binary. Each element has length 5, they're all different from each other, and none can possibly be a subsequence of another. If you wanted 1024 entries in your sequence, just make each entry 10 characters long and count from 0 to 1023 in binary. But what happens if we put a cap on the length of each string in our sequence? For instance, let's say the first term can have at most 2 symbols in it, the second term can have at most 3 symbols, the third term can have at most 4 symbols, and so on. It might surprise you that this simple change actually creates a hard cap on the length of the sequence of strings. Let's say this weren't true. So we're assuming that there's a finite cap on the length of the nth string in our sequence, and that cap is allowed to vary with n. And we're also assuming that there are arbitrarily long compliant sequences, though no infinitely long compliant sequences. Imagine that we made a tree of all possible compliant sequences. Let's start with a root node and draw an edge for each possible first term in a compliant sequence. Of course, we know there are only finitely many first terms. For instance, if there are k symbols in our alphabet and we're limited to 2 symbols in the first string, then there are at most k plus k squared possible first strings. Now, from each of those nodes, we'll draw a node for each possible second term that keeps the sequence compliant. If we're capping the second term at 3 characters, then there can only be k plus k squared plus k cubed possible next terms. But what matters is that there are only finitely many edges coming out of our current node, and that applies to every node in our tree of compliant sequences. Now, we showed that there are no infinitely long compliant sequences. An infinitely long path from the root down the tree is called a ray. So we know there are no rays, because a ray would correspond to an infinite compliant sequence. So here's where we are. We have a tree of all possible compliant sequences of strings where there is some cap on the length of the nth string. That cap means that our tree is finitely branching. In other words, there are only finitely many choices for the nth term. And we know there are no rays in this tree because a ray would correspond to an infinitely long compliant sequence, and we know those don't exist. But if we think there are arbitrarily long compliant sequences, then there must be infinitely many nodes. Why? Well, if there are only n nodes in the whole tree, then we certainly can't have a path starting at the root that is more than n nodes long. You can also think of it this way. There must be a path with at least 100 nodes, and another path longer than that one, and another one longer than that one, and so on, so there must be infinitely many nodes. But here's the problem. There is a theorem called Konig's lemma, which says that a finitely branching tree with infinitely many nodes must contain a ray. To put it another way, if there are no rays, then there are only finitely many nodes, and therefore there must be a longest path from the root. Another way to think about Konig's lemma is that if you want to cram infinitely many nodes into a finitely branching tree, you can't do it just by making the tree really wide. You actually need infinite depth. This lemma is either obviously true, or if you're like me, it's not obviously anything. Luckily, the proof is quite simple, and we'll run through it right now. So assume we have a finitely branching tree with infinitely many nodes. we're going to construct an array. First, label the root with the number 1. Now, there are infinitely many nodes in our tree, but only finitely many subtrees just below the root. So at least one of those subtrees must also have infinitely many nodes. Pick one of them and label the root of that subtree with the number 2. Again, this subtree contains infinitely many nodes, but there are only finitely many branches coming out of the root. So one of those subtrees must also contain infinitely many nodes. Again, label the root of that subtree with the number 3. Now one of those subtrees must also have infinitely many nodes, and we can continue indefinitely this way as we move down the tree. Since this process never ends, we have constructed an array with the nodes labeled 1, 2, 3, and so on. And we're done. I know this video's whole argument was a little convoluted and had some major detours, so let's recap it at a high level. We're looking at sequences of numbers chosen from the integers 1 through k. This is called our alphabet, and we are calling a sequence of single characters good if the sequence from I to 2i is never a subsequence of the terms from j to 2j for any I less than j. If there are no such I and j, then the sequence is good. And we want to show that there is a longest good sequence for every finite alphabet, and that the longest sequence is itself finite. First, we showed that there are no infinitely long good sequences. We did this by contradiction. If there were an infinitely long good sequence, then we could turn this into a sequence of strings where we take the first entry to be a sub 1 through a sub 2, then the second element to be the string a sub 2 through a sub 4, and so on. And we can declare that no string is a subsequence of a later string. We call this new type of sequence compliant. So we proved the very general result that there are no infinite compliant sequences from a finite alphabet, no matter how you generate the terms. If there were, then we could construct a sort of minimal such sequence, and then get a contradiction by strategically chopping off symbols from certain strings. So at this point, we knew that there were no infinitely long compliant sequences, and therefore no infinitely long good sequences of these single characters. Now, is there a maximum length to finite good sequences of single characters? Yes, there is. The alternative would be that there are arbitrarily long finite good sequences of single characters. And those could be transformed into arbitrarily long compliant sequences of strings, where the first string has length 2, the second has length 3, and so on. So we proved that having any cap on the length of each string prevents us from having arbitrarily long compliant sequences. Why? It's because if we made a tree of all compliant sequences where the nth entry has a maximum length, then this would correspond to a finitely branching tree with no rays, since a ray would mean there's an infinitely long compliant sequence. And then Konig's lemma tells us that such a tree only has finitely many nodes, so there's a longest path. This means if you give me a number k, then we can define n of k to be the length of the longest good sequence of characters chosen from the integers 1 to k. It's a good exercise to calculate n of 1 and n of 2 by hand. We'll do that in the next video, and then we'll try to give you an idea of just how unbelievably, unimaginably, ridiculously large n of 3 is. And if part 2 isn't out yet at the time you're watching, make sure to check out our video on uniform continuity. Thanks for watching, and as usual, leave us a comment and let us know what you think.